In a certain region, the probability of selecting an adult over 40 years of age with a certain disease is 0.02. If the probability of correctly diagnosing a person with this disease as having the disease is 0.82, and the probability of incorrectly diagnosing a person without the disease as having the disease is 0.01, what's the probability that an adult over 40 years of age is diagnosed with the disease? So in this kind of problem, the easiest way that I find is by drawing a tree. So a person may have the disease or may not have the disease. So first thing that we have is disease. Let's say, let's call it being sick. So a person may be sick. So let's say S, sick, N, not sick. And then D is diagnosed. And let's say X being not diagnosed. Okay. So now the tree that we will get is sick, not sick. So the probability of a disease is 0.02. So 0.02 that you have the disease, and 1 minus 0.02 would be that you don't have the disease. So 1 minus 0.02 is 0.98. And then if you are sick, then the probability of correctly diagnosing the disease is 0.82. So sick and diagnosed is 0.82. And therefore sick and not diagnosed is 0.18, 1 minus 0.82. And similarly, if a person is not sick, then the probability of diagnosing a disease incorrectly is 0.01, and therefore not diagnosing would be 1 minus 0.01, which is 0.99. So this is the tree we have, and we are to find the probability that a person is diagnosed with the disease. So diagnosed is this last, so D is for diagnose. So basically, we have to look at all those branches that end up with diagnose and multiply the values across. So we have a diagnosed over here, and we have a diagnosed over here. And from the beginning, in order to reach this diagnose, we have to go through this branch here and here. So it's 0.02 times 0.82. So 0.02 times 0.82. And then we add up if there are other branches leading to diagnosis. So the other one would be 0.98 times 0.01. So let's see, this is 0.0164 plus 0.0098. So that would be, okay, 164 and 98 is 262, so 0.0262. So this one is similar Okay, so now here, the probability that a person, so this is very similar to what we just did. So again, let's make the same convention, that probability that you have the disease, so it's sick or not sick. So sick is probability 0.02. Let's say not sick will be probability 0.98. And then the correct diagnosis with sick is 0.92. And not being diagnosed would be 0.08. Similarly here, if you're not sick, then the probability of being incorrectly diagnosed is 0.01, and this would be 0.99. And now here, in the previous problem, they were asking us to calculate the probability that the person is diagnosed. So we went through all the branches which end up in a diagnosis. In this problem, the difference is they're saying if the medical diagnostic is a positive result, what's the probability that the disease is actually present? So the disease present is the person being sick. So we have to find the probability that the person is sick given that the diagnosis is positive. So the if is the given. So if the medical diagnostic test has a positive result, which means the person is diagnosed with the disease. So we have to find the probability of disease actually present, which means sick, given diagnosed. So this, according to our conditional probability formula, would be probability S and D divided by probability D. So sick and diagnosed, you look at this branch. So here you are sick and diagnosed. So that's 0.02 times 0.92. Divided by in diagnosed, you have to go all the branches and end up with diagnosis. So one of them is the same, 0.02 times 0.92. Plus the other one will be 0.98 times 0.01. Okay. So now we just evaluate this one. Okay. So 0.0184 divided by so 0.652 is what I'm getting. Okay, so this one is a similar idea. Let's do it. Okay. So here, a paint store chain produces and sells latex and semi-gloss paint based on long-range sales of customers that buy 1 can of paint and 1 roller. The probability that a customer will purchase latex paint is 0.71. Of those that purchase paint, 70% purchase rollers, but only 40%. Oh, okay, of those that purchase latex paint, 70% also purchase rollers, but only 40% of semi-gloss paint buyers purchase rollers. Okay. A randomly selected buyer purchases a roller and a can of paint. What's the probability that the paint is latex? So first thing is that so let's make some notation. In this case, well, it's pretty obvious: latex paint and semi-gloss paint, and then roller, not roller. So L, latex, S, semi-gloss, R, roller, N, no roller. So initially, person will buy one of the two paints, latex or semi-gloss. So points, latex paint 0.71. So it means semi-gloss would be 1 minus 0.71, which is 0.29. And then of those who buy latex paints, 70% purchase rollers. So from here, a roller would be 70%. And not roller would be 30%. Similarly here, roller. For semi-gloss, only 40% buy rollers. So 40% buy rollers here means not roller would be 60%, 0.6. And they say a randomly selected buyer purchases a roller and a can of paint. What's the probability that paint is latex? So probability latex given that the person purchases a roller. So you see, although the given is that the buyer purchases a roller and a can of paint, but from the problem, it's clear that you buy a roller only if you buy a can of paint. So after buying paint, it's a question of whether you buy roller or not roller. So in effect, the given part is that the person purchases a roller because can of paint is always there. So if we have to find the probability latex given roller, L given R. So that according to our conditional probability formula is probability LR divided by probability R. So LR would be this 0.71 times 0.7. The roller happens through this one as well as this other branch, 0.29 times 0.4. And this ends up in 0.811. And the rest of, so basically that ends this homework.